Oh, you drop your keys, they fall. You don't think about it. It's just what happens. You feel your weight in your chair, your feet are on the floor, the moon circles the earth. The earth circles the sun. It all seems so normal, so obvious, and it's all because of gravity. But what is it? What is this thing that holds our world together, that holds us to the world? We feel it every second of our lives. But the real nature of gravity is one of the deepest and most stubborn mysteries in all of science. The story of how we've tried to understand it is the story of physics itself. It takes us from a simple apple falling from a tree to the very beginning of time and the fabric of reality. For a long, long time, people didn't really ask what gravity was. It was just the natural order of things. Heavy things fall, light things, like smoke, rise. The Greek philosopher Aristotle said things just wanted to return to their natural place. The rocks belonged to the earth, so they fell to the earth. It was their nature. And for nearly 2,000 years, that was good enough. It made a kind of intuitive sense. Then came a man named Isaac Newton. Newton wasn't just content with things having a natural place. He wanted to know the rules. The story everyone knows is about the apple falling from a tree. We imagine it hitting him on the head, and suddenly, he understands. But that's not quite how it happened. The real genius wasn't in seeing the apple fall. Anyone could see that. Newton's great leap was to wonder if the force that pulled the apple to the ground was the exact same force that held the moon in the sky. This was a radical idea. Back then, the heavens and the earth were seen as two completely different realms, governed by different rules. The earth was messy, imperfect. The heavens were perfect, eternal, divine. To suggest that the grubby, everyday pull that makes things fall was the same majestic power that guided the planets was to unite the universe in a way no one had before. Newton got to work. He developed a whole new kind of mathematics called calculus just to figure it out. And he came up with a universal law of gravitation. It's a beautifully simple and powerful idea. He said that every object in the universe with mass pulls on every other object with mass. It's a force, an invisible, universal rope. The rules of this force were clear. The more massive the objects, the stronger the pull. The sun is huge, so its pull is strong. The earth is smaller, so its pull is weaker. And the force gets weaker with distance. Not just a little weaker, but a lot weaker. If you double the distance between two objects, the gravitational force between them becomes 4 times weaker. If you triple the distance, it's 9 times weaker. It's called an inverse square law. And it worked. It worked astonishingly well. Newton's law could explain the apple and the moon. It could predict the tides based on the pull of the moon and the sun on Earth's oceans. It could describe the paths of the planets around the sun with incredible accuracy. We used Newton's equations to send probes to Mars and land people on the moon. For over 200 years, Newton's gravity was the final word. It was a force, an instantaneous pull across empty space. But there was a loose thread. A nagging question that even Newton couldn't answer. How did it work? How did the sun, 93 million miles away, know to pull on the Earth? How did this force travel through the complete emptiness of space? It seemed like magic. Newton himself was bothered by this. He called it action at a distance and admitted he didn't know the cause. He just knew the math worked. He wrote, "I frame no hypotheses." In other words, I don't know how it works. I just know that it does. For a couple of centuries, most physicists were happy to leave it at that. The theory worked, so why worry about the details? But as our measurements got better, tiny cracks started to appear. The orbit of Mercury, the planet closest to the sun, wasn't quite right. It wobbled in a way that Newton's equations couldn't fully explain. It was a tiny error, a minuscule discrepancy, but in physics, tiny errors can be the sign that something big is wrong. It was a clue that the whole story of gravity needed to be rewritten. The person who rewrote it was a young patent clerk in Switzerland named Albert Einstein. Einstein wasn't trying to fix the problem with Mercury's orbit. He was thinking about something else entirely the speed of light. His experiments had shown something very strange. The speed of light in a vacuum is always the same. It doesn't matter if you're standing still or flying in a rocket towards the light source or flying away from it. You will always measure its speed to be about 186,000 miles per second. This breaks all our everyday intuition. If you're driving at 50 miles per hour and a car coming towards you is also doing 50, their closing speed is 100. If you throw a ball forward on a moving train, its speed relative to the ground is the train's speed plus the speed you threw the ball. Light doesn't work that way. It's always the same speed. Einstein realized that for this to be true, something else must be changing. Our measurements of space and time themselves must be relative. Time can slow down. Distances can shrink. This was his theory of special relativity, and it fundamentally changed our understanding of space and time. But it had a problem. It didn't include gravity. Newton's gravity was instantaneous. It was action at a distance. But Einstein had just shown that nothing, not even information, could travel faster than light. So Newton's gravity couldn't be right. There was a speed limit in the universe, and Newton's theory broke it. So, Einstein spent the next 10 years struggling with this problem. He tried all sorts of ideas, and most of them failed. Then, one day, he had what he later called the happiest thought of my life. The thought was this: a person in free fall does not feel their own weight. Imagine you're in an elevator and the cable snaps. For the few terrifying seconds you are falling, you would be weightless. If you let go of your keys, they would just float there in front of you. Inside that falling box, there is no gravity. It's gone. Conversely, if you were in a rocket ship in deep space, far from any planet, and the rocket started accelerating upwards, you would feel pressed to the floor. You would feel weight. If you dropped your keys, they would fall to the floor. From inside the rocket, you couldn't tell the difference between this acceleration and the gravity you feel on Earth. This was the key. Einstein realized that gravity wasn't a force at all. It was the same thing as acceleration. What we feel as the force of gravity is just the floor pushing up on us, stopping us from taking our natural path through the universe. But if it's not a force, what is it? If there's no invisible rope pulling the Earth around the sun, why does it orbit? When Einstein's answer was one of the most profound and beautiful ideas in the history of science. He said that space and time are not just an empty stage where things happen. They are a single dynamic entity, a four-dimensional fabric called spacetime. And this fabric can be bent. Think of a flat rubber sheet stretched tight. That's spacetime when it's empty. Now, place a heavy bowling ball in the middle of it. The sheet warps. It sags down around the ball. That, Einstein said, is what mass does. Mass and energy tell spacetime how to curve. The sun, being very massive, creates a huge warp, a deep valley, in the fabric of spacetime around it. Now, what happens if you roll a small marble near the bowling ball? The marble will try to move in a straight line, but it's rolling on a curved surface, so its path will bend. It will circle around the bowling ball, caught in the dip. To someone watching from far away, it looks like the bowling ball is pulling the marble. It looks like a force, but it's not. The marble is just following the straightest possible path through a curved space. That is what gravity is. Gravity is the geometry of space-time. The Earth is not being pulled by the sun. The Earth is simply moving in a straight line through the curved space-time created by the sun. Its orbit is the shape of that straight line in 4 dimensions. The moon isn't being pulled by the Earth. It's following the curve in space-time the Earth creates. When you drop your keys, they aren't being pulled to the floor. They are following their natural path through the space-time that has been warped by the mass of the entire planet Earth. The only reason they stop is because the floor gets in the way. The floor is what's actually exerting a force on you, and your keys, pushing you up and stopping you from following your natural path. This new theory, called general relativity, was stunning, and it made predictions that were different from Newton's. First, it perfectly explained the weird wobble in Mercury's orbit. The sun's massive gravity warps space-time so much that it affects the planet's path in exactly the way we observe. The tiny error was gone. Second, it predicted that gravity should bend light. If a beam of light from a distant star passed close to the sun, its path should be deflected by the sun's warped spacetime. This was a wild idea. Light has no mass, so in Newton's theory, gravity shouldn't affect it much, if at all. In 1919, during a solar eclipse, the astronomer Arthur Eddington took photographs of the stars near the sun. When he compared them to photos of the same stars taken at night, he found they had shifted their position. The light had been bent, just as Einstein predicted. The news made Einstein an international celebrity overnight. The old theory was dead. Gravity was not a force. It was the shape of reality itself. Einstein's theory made another, even stranger prediction. If a massive object, like 2 black holes orbiting each other, were to move violently, it should create ripples in the fabric of space-time. These ripples, called gravitational waves, would travel outwards across the universe at the speed of light. For a century, this was just a theoretical idea. The ripples were predicted to be incredibly tiny, so small that Einstein himself doubted we could ever detect them. But in 2015, we did. 2 giant detectors, one in Louisiana and one in Washington State, part of the LIGO experiment, felt an almost infinitesimally small stretch and squeeze of space. It lasted for just a fraction of a second. When scientists analyzed the signal, they found it was the perfect signature of two black holes, each about 30 times the mass of the Sun, spiraling into each other and merging in a distant galaxy over 1 billion years ago. The collision was so violent it sent a storm of gravitational waves across the cosmos. For a brief moment, the event released more energy than all the stars in the observable universe combined. And we felt it. We heard the sound of space-time ringing. It was the final triumphant confirmation of Einstein's theory of gravity. So, is that the answer? Is gravity the curvature of space-time? For now, yes. General relativity is the best description of gravity we have. It's been tested again and again, and it has passed every single test with flying colors. It governs the lives of stars and galaxies. It's even practical. The GPS in your phone has to account for the effects of general relativity. Time actually runs slightly faster for the GPS satellites in orbit than it does for us on the ground because gravity is weaker up there. If the system didn't correct for this, your GPS would be off by several miles every day. But the story isn't over. Just as Newton's theory had cracks, we now see cracks in Einstein's. The problem is that Einstein's theory describes the universe on the grandest of scales. It's the theory of the very big. But in the 20th century, we also developed another theory, quantum mechanics, which is the theory of the very small. It describes the strange probabilistic world of atoms and particles, and quantum mechanics is also incredibly successful. It gave us lasers, computers, and nuclear energy. Here's the problem: the two theories don't work together. They are written in different languages and are based on completely different principles. General relativity is all about smooth, curved geometry. Quantum mechanics is about discrete, jumpy packets of energy called quanta. When you try to use them together in situations where you have a lot of mass crammed into a very small space, the math breaks down. Spits out nonsense like infinities. And where do we find these situations? Two places. The very beginning of the universe, the Big Bang, which was an unimaginably hot and dense point. And in the heart of a black hole, a place called a singularity, where gravity is so strong that space-time is thought to be infinitely curved. To understand these ultimate extremes of the universe, we need a new theory. We need a theory of quantum gravity. Finding this theory is the biggest challenge in physics today. It's the Holy Grail. There are a few main ideas about what it might be. One idea is called string theory. It suggests that if you could zoom in on a fundamental particle, like an electron, you wouldn't see a point. You'd see a tiny vibrating loop of energy, a string. And just like a guitar string can vibrate at different frequencies to produce different notes, these fundamental strings vibrate in different patterns to produce different particles. An electron is one vibration, a photon is another, and the theory predicts one particular vibration would give rise to a particle called the graviton. This would be the quantum particle of gravity. In this view, the smooth fabric of space-time we see is actually made of a web of these interacting gravitons. Gravity, then, would be the exchange of these particles. It would be a force again, but a quantum force, fitting in with the rest of physics. String theory is mathematically very elegant, but it comes with a lot of baggage. It requires extra hidden dimensions of space, and so far, we have no way to test it experimentally. Another leading idea is called loop quantum gravity. This theory takes a different approach. It suggests that space-time itself is not smooth and continuous. It's quantized. Just like a picture on a screen is made of tiny pixels, space-time is made of fundamental, indivisible chunks. You can't have a smaller piece of space or a shorter moment of time than these elemental units. In this picture, space is a network, a web of connections between these atoms of space-time. Gravity isn't a property of some added field. It's a feature of the network itself. The geometry of space-time emerges from the way these loops and nodes are connected. It's a radical idea to think of space and time as being built from something more fundamental. As if that wasn't complicated enough, our observations of the universe have thrown two more giant mysteries into the mix, and both of them involve gravity. The first is dark matter. When we look at galaxies, we can measure how fast they spin. We can count up all the stars and gas we can see, calculate their total mass, and use Einstein's or even Newton's theory of gravity to predict how fast they should be spinning. But when we do this, we get a huge shock. The galaxies are spinning way too fast. The stars on the outer edges are moving so quickly that the gravity of the visible matter shouldn't be nearly enough to hold them in orbit. They should be flying off into space. For them to be held together, there must be a huge amount of extra mass, a huge amount of extra gravity that we can't see. We call this stuff dark matter. It's not just dark like a planet that doesn't shine. It's completely invisible. It doesn't seem to interact with light or any other form of normal matter in any way, except through gravity. We know it's there because we can see its gravitational effects. We can see its gravity bending the light from distant galaxies. We can see it holding galaxies and clusters of galaxies together, but we have no idea what it is. All the stars, planets, gas, and dust, everything we've ever seen, makes up only about 5% of the total stuff in the universe. About 27% is this mysterious dark matter. We are surrounded by an invisible sea of something, and its only tangible property is its gravity. The second mystery is even stranger. It's called dark energy. For most of the 20th century, we thought the expansion of the universe, which started with the Big Bang, was slowing down. The mutual gravitational pull of all the galaxies should be acting like a brake. But in the late 1990s, astronomers discovered the opposite. The expansion of the universe is accelerating. It's speeding up, something that's pushing everything apart, overwhelming gravity on the largest scales. We call this mysterious anti-gravity force dark energy, and we have even less of an idea what it is than dark matter. It seems to be a property of empty space itself. As space expands, more space is created, and with it, more of this dark energy, which pushes things apart even faster. It's a runaway effect, and it is the dominant thing in our universe. If you add up all the matter and energy, about 68% of it is this dark energy. So, what is gravity really? It's the familiar pull that keeps our feet on the ground. It's the invisible force Newton described, a universal attraction between all things with mass. But that's just a shadow of the truth. It's the curvature of space-time, the very geometry of our four-dimensional reality warped by the presence of matter and energy. It's what tells planets how to orbit and light how to bend. This picture, Einstein's picture, is our best current description. It's a theory of profound beauty and proven power, but it's also incomplete. It's the source of the deepest puzzles in modern physics. To truly understand it, we need to know how it works in the quantum world, inside a black hole, at the birth of the universe. It might be the effect of tiny vibrating strings in hidden dimensions. It might emerge from a pixelated quantum network of space-time itself. We don't know yet, and it's the only way we know about the vast, invisible universe that surrounds us. It's the clue that tells us 95% of the cosmos is made of dark matter and dark energy, things we have yet to comprehend. The simple act of dropping your keys connects you to all of this. It connects you to the motion of the planets, the bending of starlight, the collision of black holes, the birth of the universe, and the greatest unanswered questions of science. Well, gravity is not just something that happens. It is the shape of the stage on which everything happens. And we are still just beginning to understand what that shape really is. The story is far from over.